Cheers! Well, we are back, and this time I'm going to share with you an everyday example of the gradient vector. Well, you guessed it right. You can experience it or perhaps measure it if you have the right equipments in just a glass of water. So let's see how. Well, we've talked about how a fluid can be treated as a continuum. We also have a video showing you an experiment on how you can see divergence and curl patterns and very other interesting patterns in just simple two-dimensional fluid flow that you can create in your own home. And for a full course on the introduction to differential calculus and experiments such as these, sign in to www.dsigma.in and register for our course and support our channel. Now, today, we're going to extend this idea, or rather, we're going to just think a little bit more about fluids. By the way, we're going to make a separate video series on fluids, introduction to fluid mechanics for all those of you who are interested. But for today, I'm just going to show you how the gradient vector, uh, and we've given one example of the gradient vector using a Hill model. Again, you can look at the course on the introduction to differential calculus in case you've missed that. But I'm going to give you a more everyday example of how the gradient vector is useful and how we come across it in measuring or in coming up with simple explanations of everyday things. And one such example is how the pressure varies along the direction of the gravity field in a glass of water. So let's see how that happens. Now, we're not going to go too much into the detail of the physical description of a fluid, but suffice it to say for now that we can describe a fluid as a continuum medium, which means we'll assume that differential calculus can be used across different points in space and time when we are thinking about fluids. So for instance, I might have some kind of a fluid flow like this. Let's say this is 2-dimension. I can define a pressure perhaps at this point, and let's say this is 2-dimension. Let's for simplicity assume that this is 2-dimension. So I can define a pressure at this point, x, y, comma, t, and I can go a tiny step away from here to the point which is at x plus dx, y plus dy, and maybe at the same time or a different time. So you can define a pressure at x plus dx, comma, y plus dy, comma, t. Pressure is just one example of a thermodynamic property or a macroscopic property, which we can define for a fluid. Likewise, you can define other properties of a fluid. So you might have what is called the density of a fluid. Again, we'll assume that it's well defined in space-time. It's not very obvious when I say that we can define the pressure at a point in a fluid. What do we mean by a point in a fluid? And again, we'll do a full course on fluid mechanics, but for now, let's just think of a continuum space-time medium, and with the assumption that we can measure pressure, density, perhaps even the velocity field. Again, the velocity would be a field, like you can measure the velocity of fluid at different points in space, and it might vary in time, right? So you can measure what is called the velocity vector at x, y, t, and perhaps you can also have the z coordinate, right? So these are all examples of fields, right? These are all examples of fields which you can associate with fluids. Now, one such example is the pressure, right? And we're going to ignore flows for now. So just think of a glass of water or a static condition where the fluid is not flowing. Maybe you're just storing it in a tank. And let's think about defining the pressure across, say, a tiny element of that fluid. So by that, I mean, let's maybe do it more generally. Let's consider a three-dimensional fluid element, right? So perhaps I'll take a simple three-dimensional cube, and this is an infinitesimal cube like this, right? And let's say the center of this cube, maybe I'll use some other coordinates somewhere here, is the point x, comma, y, comma, z, right? And this is some fluid that's there. Maybe it's in a static condition. Maybe you're holding it in a tank. And I'm just picking out one element, one differential volume in that finite volume. That's kind of the idea we have in mind here, right? So let's say this differential element is located at the point x, y, z, right? So time is not a variable for us because we're just assuming static conditions, no flow. And perhaps we can define axis. So maybe this is the, maybe I'll call this the x-axis, that's the y-axis, and that's the z-axis, right? So let's look at one of these faces, maybe this one, and another face, which is say this one. So these two faces are sort of in the YZ plane, right? This is the YZ plane. This is the YZ plane. It's only the X coordinate which is changing as I go from one face to the other, right? And again, if you believe in this kind of a description that we can define pressure at different points in the fluid medium which we are considering, we can define a pressure right here, right? So maybe I'd call this pressure. Perhaps I should use a black pen. So we can call this pressure at this face. And let's say this is the x direction, but this element has length del x, right? So we're considering it an infinitesimal element. This y-axis has length del y, and the z-axis has length del z. The center point is at x, y, z. We'll assume that the cube is such that the faces on either side are at a separation of del x by 2. So the length of one side along the x direction is del x, and then if you want to go to the one of the faces, it's at minus del x by 2. The other faces is at plus del x by 2. So x minus del x by 2 and x plus del x by 2, right? So let's say I want to define the pressure here, and again we'll assume that the pressure across this entire face is constant. So right, so we just assume for now that I can define the pressure right here at the center and call that pressure x minus del x by 2 comma y comma z, right? So that's the pressure, say, across at this point, and it's roughly constant across this entire face. That's the pressure here. And likewise, we can define the pressure along this face. Now, this face is at a separation of del x from this face, right? So the pressure there will be P at x plus del x by 2, comma y, comma z, right? In the same way, we can define the pressure here and study the change in pressure from this face to this face, where only the z coordinate is changing, right? And in the same way, we can define pressure variations along the y direction. So we can consider pressure here and here, where only the y coordinate is changing, right? So let's look at, now, if you remember some high school physics, force being exerted on this fluid element would be pressure multiplied by the area where that pressure is being applied, right? So I'm going to assume that across this face, if I'm defining the pressure to be P x minus del x comma y comma z, then it's constant across this entire face. Okay. With this, the x component of the force being exerted on this fluid element would be, now remember that pressure is something which is compressing this fluid element from all sides, right? So on this side, the pressure is compressing. On this side, the pressure is compressing like this. So if you want, I can just draw the diagram again. So let's say this is the x, this is the face which is normal to the x direction, this one, and this is the other face normal to the x direction. So we'll assume that the pressure here is like this, and the value or the magnitude of this pressure is Px minus del x by 2, comma y, comma z. The pressure here is also compressive. It's pressing, right? So it's P x plus del x by 2, comma y, comma z. And so I want to calculate the net force in the x direction, right? The other two faces are pointing in y and z direction respectively, so they don't exert a net force in the x direction. So the net force in the x direction, maybe I should write it again here. Net force in the x direction would be this pressure. Now if this is the positive x direction, then this pressure is along the positive x direction. The area of this face is del y comma del z, because that's the dimension of the cube that we're considering, right? So the force in the x direction would, coming from this face alone, would be P, the pressure, x minus del x by 2, comma y, comma z, multiplied by the area of the face, right? And the area of the face is del y, del z, right? So that's the positive x component of the force being exerted on this fluid element. Similarly, so let me just call this phase 1, and let's say this is phase 2. The force being exerted on phase 2, now notice that this pressure is pointing in the negative x direction. So the force being exerted will be negative of the pressure being exerted there, and the pressure is P x plus del x by 2, comma y, comma z, and again the area of the face is just del y, del z. Fairly okay? Now, If you remember the discussions we've had on partial derivatives, and again, I'm assuming that differential calculus is valid for this medium, which means that the pressure is a continuously varying variable. I can do a Taylor series expansion, and we have had an in-depth discussion of Taylor series for functions of more than one variable in the course on the Introduction to Differential Calculus that's available on the website dsigma.in. So do check it out, give us your feedback. Now, if this differential calculus is valid, and let's say del x, del y, del z are tiny, I can do a Taylor series expansion of this field, this function. Now notice here, it's just the x coordinate which is varying as long as we're just considering forces in the x direction, right? So if I do a Taylor series expansion of this, I can write this as px, that's the first term. Maybe I should write all the coordinates just for completeness. So we have p, x, comma, y, comma, z. That's the first term. We still have del y, del z, minus, I'll have the partial derivative of p with respect to x. We have del x by 2, del y, del z. So that's the first order Taylor series expansion. We're just going to take the first order linear Taylor series expansion. From the second term, I will again have minus p, x, comma, y, comma, z, del y, del z. And then there is a plus here. So that will again be a minus dou p, dou x, the partial derivative of p with respect to x, del x by 2, del y, del z. Now notice that these two terms are the same, so they just cancel out. And so what we're left with is a combination of these two, but they're just the same terms, right? So they add up. And so we'll have minus dou p, dou x, del x, del y, del z. That's the net force along the x direction, right? Now, if you do the same kind of analysis on the y face, the face which is normal to the y direction, and the face which is normal to the z direction, you'll see that we can pick up force along the y direction as minus dou p, dou y, and we'll still have same terms here, same differential terms. And notice, by the way, that this is a cube of dimension del x, del y, del z. So that this entire thing is just the volume of this cube, which maybe perhaps we can write as d tau, or since I'm not using d, I'll just write this as del tau. So that's the volume. That's the volume. Similarly, the force along the z direction would be minus dou p, dou z, del tau. Therefore, the total force on this entire fluid element, now force is a vector, pressure is a scalar, right? So the total force will have these three different components acting in the I, J, and K directions. So the total force is Fx along I plus Fy along J plus Fz along K. And this, if I combine all of these, then I can write this total force as minus dou P, dou X, I minus dou P, dou Y, J minus dou P, dou Z, K. And the volume element is just a common factor. That's the total force acting on this fluid element. Now, if you remember the discussion on gradients, you'll notice that this thing that we've just figured out in the square brackets is nothing but the gradient, negative of the gradient of the pressure field. Pressure is a function of x by z. So this is a negative of that gradient times the volume of this element. So if I divide this force by the volume of this element and call this maybe a small symbol like F, which denotes force per unit volume, then the force per unit volume is nothing but the gradient of the pressure. Right? So this is very interesting. Any forces which exist in a fluid, by the way, this is an example of what is a surface force, which means it acts on the surfaces of a fluid element. You can also have a body force, which acts on the volume, so to say. And that, for instance, gravity is an example of a volume force. But any forces which arise due to pressure would depend upon the gradient of the pressure. So it's the force that comes from pressure only occurs when there are changes in the pressure field. Now, if you remember the discussion we have had on gradients, you will also notice that the gradient points in a direction where the change in the field is the highest, right? Which means that, let's say I have a glass of water, which is what we started off with, right? Now the force, and that glass of water is just sitting on the table. The only sort of force which is acting, the kind of an external force which is acting is the force of gravity, and that acts vertically along the along the height of the glass of water, right? So the maximum changes that we will see in the pressure field would occur in the direction which is aligned with the direction of the force vector, right? So what this expression tells us is that the changes in the pressure will be highest along the direction of gradient of P. The gradient of P is nothing but the force vector. Therefore, the changes in pressure, the maximum changes in pressure we'll see would happen in a direction which is aligned with the force vector. And for a glass of water, that will be along the direction of gravity, which is along the vertical height of the water column. Now, also remember that we had this discussion during the course on the introduction to differential calculus that normal to this direction, right? There is a direction where the pressure doesn't change at all. And maybe again, I refer you to the course, and these are sort of contour lines. So for a glass of water, these contour lines are orthogonal to the direction of the gradient vector. And this orthogonal direction is nothing but the horizontal slices or horizontal planes in that glass of water, right? So along a horizontal slice of the glass of water, the pressure doesn't change at all. Whereas as you move vertically up and down because of gravity, the pressure, you will observe changes in pressure. And this is something we have studied in school, right? For instance, at the top layer of the glass of water, the pressure is just the atmospheric pressure, whereas as you go down, the pressure becomes the atmospheric pressure plus rho g z, where z is the height of the water column, right? But along a horizontal plane in the glass of water, the pressure remains constant. And so this is an example of how the gradient vector can be used to give us another perspective on these physical observations. So I hope this video was of some use, and hope to catch up with you on more such informative videos on how we can apply some of the things in differential calculus for understanding everyday phenomenon that we see around us. Thanks for watching.